Welcome to our power quality improvement technique. Today we require to discuss about the PWM voltage PWM for the voltage source converter, that is a control technique required for the voltage source converter. Voltage source converter is a integral part of your active compensation, which we will see after few classes as a series compensation, shunt compensation. So, for this reason we require to revisit the control technique or the pulse width modulation technique required for the voltage source inverter. So, most common voltage source converter is that 3 phase 6 steps offer simple control with the lower harmonics. So, for this reason we go for the we do not require the return wire for 3 phase 3 wire system, and for this reason we go for the 3 phase, that is a worldwide convention. And once you feed it, you consider that uncontrolled rectifier. So, it is essentially the 6 steps. You will find that there is a harmonics of the that is a 6n plus minus 1, and the output voltage will have a ripple of the 6 steps in a cycle, because one pair of diode conducts from the 120° mode, and that is the common aspects of all those adjustable speed drive, because there is a front end may be a passive rectifier. So, what does happen? It leading to high distortion of the current value, and PWM inverter on the other hand offers better control of the output voltage than the 6 steps inverter. Because if you know that, if you have studied the full control converter for triggering angle in continuous conduction mode, for triggering angle for load current being constant, alpha 90°, 0 to 90°, it is in the converter mode, and alpha 90 to 180°, it is in a inverter mode. That is the mode of operation for the inverter, and that is the your 6 pulse inverter. Instead of that, we require to go for the PWM inverter. The logic behind is that PWM inverter offers better harmonic control than the 6 steps inverter. PWM, why? Because one of the necessary conditions of the 6 pulse inverter or the 6 steps inverter is that your load current required to be continuous in DC side converter or the AC side. So, for that reason definitely you require to have a very high value of the inductor. So, that is a prerequisite, and thus makes the system costlier, and also there is sometime maybe a commutation failure. This is a challenge once you go for the thyristor drive. So, you depending on the switching, you may go for the IGBT based devices where switching frequency can as high as a 10 kilohertz, or the GTO based drives where the frequency will be around 1 kilohertz, but either of the cases PWM is preferred, and why it is so we will see in the subsequent lectures. So, PWM will also provide linear control output as desired reference. Let us see that how it is been done. So, we can broadly classify the PWM technique as a sinusoidal PWM, that is the common PWM, and we can have a SHE we say in abbreviation, that is called the selective harmonic elimination, and this is quite useful in the power quality applications for the grid fed inverters, because you know that you will be subject, if it is a 6 plus converter, mainly if you use 6 n plus minus 1 are the dominating harmonic, and thus how you can mitigate those harmonics from this power quality. So, so you can go for, that is 5th and 7, 11 and 13 and so on. So, you can go for SHE. And another is important aspects of the PWM category is that space vector PWM or space vector modulation technique, there we can use higher utilization of the DC bus voltages, and thus you can get a better modulation index. What is modulation index? I am coming after few slides. And thereafter it will be followed by instantaneous current control PWM, where control will be on the current side. It is called, mostly it is preferred, it is called current control voltage source inverter, full form will be. Another, you will see that this is a hysteresis band current control PWM. It will be mostly used and in your D-STATCOM or the shunt active power filter for its simplicity, but there is a complexity of it in a different domain, because you throw this complexity somewhere and you do not care and you feel that you are happy, but it is not so. So, anyway, so let us move to the first. There are other PWM which you have studied in your basic power electronics courses, trapezoidal PWM, square wave PWM. For sake of time, we are not going to it and we are not using nowadays. And for this reason, we are straight away going for the sinusoidal PWM technique. So, that is why it is the most common PWM approach is sinusoidal PWM. In this method, a triangular wave is compared to a sinusoidal wave of the desired frequency, and the relative levels of the two waves is used to control the switching devices in each phase of the inverter. Let us see that how does it work. So, this is the its single phase version, and here it is implemented. This configuration is called the half bridge configuration. So, here we, and generally if it is a voltage source inverter, current is bidirectional depending on the whether it is a leading lagging, only it will be unidirectional in unity power factor operation. So, for this reason we require to provide the anti-parallel diode with it, and generally we have to provide the central trap by splitting this midpoint by the two same value capacitor O, and that fictitious midpoint required to be available into the system. And depending on the switching, you get a square wave and we require to get a PWM wave. Same way, this is the 3 phase version of it. You can see that these are been implemented by the bidirectional current, because it does not have a reverse current blocking capability because of the diode, and it can only have a forward current blocking capability, forward voltage and the current blocking capability. So, it is a bidirectional current and the single direction current blocking capability. This capability is required here. So, this is the configurations of your voltage source inverter, 3 phase voltage source inverter. Now, you require to this carrier wave, for sake of understanding, has been kept the frequency very low. Generally it is quite big. So, its carrier frequency generally around 20 times more than in case of the GTO, because if it is a 50 hertz, your carrier frequency is in around of 1 kilohertz, and in IGBT it generally more than 100 times, it may be 5 kilohertz. So, the logic is this VAO is the modulating signal and Vt is called the carrier signal. Then if VAO is greater than Vt, then T plus, that is the, if you go back this switch, T plus will be on and otherwise T off will be off, and ultimately you will get the load will get the voltage VAO, that is half of the Vd, that is the case of the half bridge configuration, but if you have full bridge configuration you get full Vd. Similarly, if VAO is less than Vt, then the lower switch will be on or T minus will be on and T plus will be off and load will get minus VAD, thus you will get this kind of pulses. So, this is the pulses, and since this is operating this way, so you will get this pulses like that. This is for one of the phases, and if you combine, so you get A, B, C, all the phases. So, these are the VAO is the phase voltage. Similarly, so if you combine A and B, so you get the line voltages here, and line voltage will have this PWM pattern, because you can see the pulse width is modulated. Ultimately, it will be equivalent to your this sine wave, sorry, this magnitude has to be less. So, so this volt area of this sine wave and these buildings has to match. So, there will be an instant voltage difference between this sine wave and the exactly actual voltage has been injected. So, and that is the cause of the harmonic, because there is an instantaneous error and that has been filled, that cavity is filled by the harmonics. So, and if you talk about that, let us go back and to this circuit. So, and if you talk about the neutral voltage, then you will get, this is basically phase voltage, this is basically VAN, and ultimately one observation you can see here, this is bipolar, because it is switching on plus VDC and minus VDC phase voltage, but the line voltages are unipolar. So, let us define few terms, for sake we will be using those terms very frequently. The triangle waveform, switching frequency, sometime it is called, or that is called sometime called carrier frequency also. That term is derived from this communication, also called the carrier frequency, and the control signals F, sometime it is called modulating signals or modulating frequency. So, the ratio of the amplitude of this Vp by Vt, that is peak of the amplitude of the control signal at the peak of the amplitude of the triangular wave, that ratio is called the modulation index, and frequency modulation index ratio is Fc by F. Let us consider that it has a switching frequency of 10 kilohertz and this has a the frequency is 50 hertz. So, it is 200 times is this MF. Now, what happened? This is the harmonic spectrum. Here, if you do this FFT of this waveform of, please go back, this one, you will get this kind of waveform. It is for this ratio 0.8, that means this modulating index is 0.8 and MF is 15, that means it is around 750 hertz for 50 hertz supply, for 60 hertz supply it is 900 hertz. So, what we will find that there is a modulation index of 1 and thereafter there is a no frequency available and no frequency strength will be available, and after that as you understand that this strength is essentially is a if it is a 750, if it is a 50 hertz. So, there will be a 2 side band. So, it is 800 and this one will be your this 100 will be 700. So, and this band will be the 750. So, ultimately what happen in case of the square waveform, you get first harmonic, fifth harmonic, 7th harmonic, 11th harmonic, 13th harmonic and so on. But here stator wave first you get the 50 hertz for Indian context, thereafter it will be shifted to, but with the same magnitude with a 750 hertz, that amount is given by this MF kind of shift, and there will be a side band, that magnitude will be generally 1/3 of 0.8. So, 1/3 of the MA, here it is 0.8. Similarly, at 2 MF you also get 2 harmonics. So, here also at 150 1550 and 1450 you will get another 2 spectrum, same way so on. Ultimately what happen, it shifts the spectrum at the higher frequency region. So, thus what happen, since your power system itself is a low pass filter. So, this high frequency component can be eliminated by the very small size filter, and thus your drives become compact. But disadvantage, of course, since there is a high frequency component, there are huge amount of the conducted and the radiated emission. So, EMI EMC will be a great demerits of this PWM. But as far as the THD is concerned, removing getting a better THD, voltage THD will be the same, it is not very good, because you have a whole sort of thing. But since you are sending, let us go back to this, the voltage waveform through the through an inductor. If you are feeding, let us say you are driving an AC drive, and ultimately it has a wire has not got an inductor. So, for this reason current will be sinusoidal, but and thus what happen, you can see that for fundamental it will offer some amount of impedance. Once for this next this one, this will employ the M into Z, thus current will be reduced by M times, and thus current THD will be lower in case of the PWM. That is a biggest advantage of this PWM. But of course, you pass this buck somewhere. If you are concerned about EMI EMC, this method is not at all suitable. So, we can say something about it, that is the sinusoidal PWM inverter has some points to be discussed here. At high switching frequency or the carrier frequency, the nominal leakage inductance of the machine will effectively filter out the inverter line current harmonics. That is what I was saying. So, your inductors present into the line, or you may require to put a small filters to, otherwise what will happen, it will kill the insulation of the machine and machine life will come down. So, for this reason it is advisable to put a filter before you are putting to the machine, so that you almost get apply a sinusoidal waveform, because sinusoidal waveform is something like best suitable from this AC machine, because rate of change of voltage is sin theta, if you differentiate it is cos theta, and it is best because once you are 90 degree. So, your cos value is 0. So, at a high voltage rate of change of voltage is 0. But since you got a PWM pulses, so your dVdt is very high, and due to that leakage current will flow, and there is a capacitance in between different point of the machines, because there is a different voltage the different part of the machine, and you have to ground it because of this operator will operate, and ultimately C dVdt is the current. So, high leakage current will flow, and that will essentially damage the insulation of the machine. And for this reason it is advisable to put a filter, so that you filter will eat up the Henlock. So, filter will eat up this harmonic part and try to increase and try to feed the good quality supply to the machines, otherwise machine life going to be degraded. Okay. So, but another disadvantage is that high FC leads to higher switching losses. There are these power electronics devices, as you know, there are two major losses. One is definitely the conduction losses, and another is a turn on and turn off losses, unless you make the switching soft. But if you try to make it turn on and turn off losses, that is called 0 voltage or the 0 current switching. In that case also there are a lot of demerits. You have to put a extra resonant bank, and for this reason let us assume initially that we are having a Hertz switching, that when you got a turn on and turn off losses. If you have a 750 hertz, then of course you are cutting this waveform 750, you are cutting this waveform this many much of times. So, you are cutting here, you are cutting here, you are cutting here and cutting here, and accordingly the pulses will be generated. So, more the so there is a turn on and there is a turn off, there is a turn on and turn off. So, in that way there will be a 750 turn off. If it is 20 kilohertz, you will have a 20,000 turn off and turn on. So, for this reason, so you can see that how it has been calculated. So, there will be a huge turn on and turn off. So, because how many cuts will be there, it is not about the switching frequency, but how many cuts. So, here you can see that this carrier frequency is 3 times more. So, it is 3 f and this is f. So, you have a 6. If it is 200, then it will be 400 turn on, 400 times turn on and 400 times turn off. So, there will be a huge losses. So, for this reason we will turn this turn on and turn off losses will increase or switching losses will increase, but you will get an advantage that you require the size of the filter that will be low, but device also has to support that switching frequency. IGBT, you know that you had a current trail, and thus due to the current trail, huge current trail than the MOSFETs. So, for this reason you cannot, unless you cannot put it on another cycle unless the current trail is finished. So, for this reason most of the modern IGBT is limited to its switching frequency in and around 10 kilohertz. So, another is that third harmonic injection modulation. This is quite interesting. Let us go to the whiteboard, you have a sine wave and you have a third harmonic to be superimposed on it. Beauty of it that third harmonic will finish here, here and here. So, you have third harmonic like this and they are co-phasor also. So, ultimately you have a 0 crossing here and ultimately you have a 0 crossing here. So, beauty of it is that after 30 degree you got a this contribution, and if the magnitude, if it is 1 let us say, and it will be around 0.5 or something, we have to fix it up. So, there is a way to calculate what should be the amount of, we say, contamination. And if you contaminate, then what will happen? The waveform will be a flat topped one, and this waveform has a peak, will be higher peak than this, and generally the modulation index what maximum you get is 1.16. So, in that way you can use your DC bus voltage better, because you know ultimately what you get, the magnetic amplitude, it is a m into VDC or VDC by 2 depending on whether you are using the half bridge or the full bridge configuration. So, theoretically if it is m equal to 1, the maximum value of the fundamental peak is at, for the half bridge it is 0.5 Vd, and for a square wave what happened, you know that it is 4 Vm by 2 pi and it is 4 Vm by pi for the full bridge. So, what happened then, the maximum value can be increased to 0.9 basically, you can neglect this 0.7 part, that is for the square wave injection by injecting the third harmonic. That is the enhancement of the DC bus you get. Normally you, if you have a one modulation index 1, you get 0.785, and with the third harmonic that has a quantity, whether there is a two issues. If you use third harmonic, the THD generally degraded. So, there is a condition of how, what should be the amount of the contamination for injection of the third harmonic. Generally if it is 1/6, the THD is minimum. Generally if it is 1.25, 1/4, then you have a maximum utilization of the DC bus voltage, that is your 0.97 V peak by injecting third harmonic. And this is a common mode voltage, as you have seen that third harmonic, you know, you have studied in your basic transformer courses, that they are lying only on the surface, and for this reason circulating current will be there, and since it is a common mode voltage, it does not flow if you do not connect the midpoint of the capacitor in 3-phase 3-wire system, and it does not affect the torque production. That is the beauty of it. And if you go to this modulation index above 1, it is called the over modulated region and gives nonlinear control and increases the harmonics, but DC bus utilization voltage does not increase as much. So, it is kind of hysteresis curve, we will come to the next figure, and it is limited to, you can give these equations. So, it gives a nonlinear control and increases harmonic, but results in greater output. So, it is Vd by 2, it is it should be less than the phase voltage, and that is limited to 4 Vd by 2 pi or pi depending on half bridge or full bridge. For full bridge I have told you it will be pi, for the half bridge it will be 2 pi for modulation index. In this is a case of the square wave inverter, where you get the voltage 4 Vm by 2 pi. Now, this is the examples, you know. So, this is once you operate in a synchronous domain. Another issue is that I told you, you know, you have calculated the harmonics, it can be 15. If it is, if you have a 50 hertz supply, what happen if I set the switching frequency? Let us say you have taken the drive from the USA and there it was operating at a 60 hertz supply, and your switching frequency was 720, it was running extremely fine. Now, all of a sudden you brought it to the 50 hertz supply and you got a 72 hertz switching, then what will be the problem? So, will there be any problem? So, that is an issue. So, we have to look and revisit it, and it is desirable to have is an integral. However, as fundamental frequency decreases, Fc would also have to decrease, or to decrease not desirable terms of the machine's harmonic loss. You know, if you have this kind of cases, it generates the intra-harmonic. So, you will have some subharmonics issues also, and this subharmonic issue is a very big problem, because you know that it will elimination of this low frequency will be very difficult, and for this reason it will increase the losses, and for our discussion Fc would also have to decrease not to the desirable level in terms of the machine's harmonic loss. An optimal choice of Fc different S is given below. This is the value of the Fc. Generally we call till 0.5 as asynchronous region, 50 hertz. Thereafter you got 2 peaks at 0.75 and P2. Thereafter you got this, this is called the asynchronous region, and here you will get a constant torque, and for the ratio F by Fb more than 1, here it will be a constant frequency region, and ultimately you will get a constant power. So, this is the case, but you require to have a integral multiple of it, and preferentially we should have a odd symmetry, that is what we generally take into the consideration, and try to make the multiple integer of the odd symmetry, then odd harmonic will be present. Thank you for your attention. We shall continue to our discussions with the PWM technique for the voltage source converter.